Hello friends, welcome to another lecture of EMT for BSc and MSc students. In this video, we are going to discuss that electric field E and magnetic field B. Okay, these are in same phase in electromagnetic wave, and using Maxwell equations we're going to prove this too. These two are in same phase and their ratio is constant. Okay, that's what we're going to prove. So now before we start, please do subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you, and hit the thumbs up button. And if you want to follow me on Insta, this is my Insta ID, OJHALAKHYAJIT123. This is my Insta ID. You can follow me on Insta. And I have already started solving previous year's questions of 6th semester. So stay connected. So now let's start. You see, from Maxwell equations in free space. So there were 4 equations. We have got this relation in Maxwell's equation. From Maxwell equations, we have got this equation that curl of electric field E and time derivative, partial derivative of B with respect to time with respect to t, and B is the magnetic field, which is also can be written as mu naught H, right? So that can be written in this way also. If we want to write, then minus mu naught del H by del T, right? You can write this way also. This is suppose equation 1. So if you have watched all the previous lectures, or hope you know what are the meaning of the symbols that I am using here. Okay, so now you see, let us consider that you see solutions of EM waves. We have got the equations of EM wave. We have already discussed. I have given the link of that lecture in the description box. If you are not aware of that EM wave equations, then please do click the link and watch that video. Okay, equations of electromagnetic waves in free space are given by del square E minus epsilon naught mu naught epsilon naught, then partial derivative of E with respect to time t is equal to 0. This is one equation, and in terms of magnetic field we can write this, right? Both are in the same form, right? Hope you have understood this. A is equal to 0, right? Just give me a second, let me write it properly. Okay, so these are the equations. Okay, now you see their solutions are given by respectively solutions of these 2 equations. Okay, solutions of equation number 2 E. So I have considered that let me consider that the EM wave is propagating along x-axis. Let me write here, just give me a second. It is propagating along x-axis. Traveling in positive x-axis. Let me write that way. Okay, then we can consider E x comma t that's going to be E naught e to the power I kx minus I omega t. Okay, or we can take the I common, we can write this way as well. Sorry, we can write this way. Okay, so here you know k is propagation constant. Right, hope you know these things. Now you see, similarly in case of magnetic field we can write this H naught e to the power I omega t, and we are to prove that E and H or E and B are in the same phase. But first, initially, before we prove that, let me consider there is a phase difference between these two. That is, suppose alpha. Let me take this is beta, alpha beta phase difference. Okay, let me take alpha beta phase difference between E and B or E and H. Let me take that way. Okay. So hope you have understood this. Now you see, these two solutions, must satisfy the Maxwell equation, right? It must satisfy the Maxwell equation. So we have to write this equation number 3. Okay, 3 must, or let me write this way instead of writing 3. Okay, let me give this equation number 3. So these solutions must satisfy equation number 1. What is equation number 1 here? This Maxwell equation. Okay, right. So must satisfy equation number 1. So what was that equation number 1? Let me copy this equation number 1. You see, so let me write here. This is the equation number 1. Okay, so now first you see, let me write this. You see what we can do here. You see, this E vector can be written in this way. It must have 3 components: x component, y component, and z component, right? Similarly, this H vector, it must have this x component, y component, and z component, hz, k cap, right? So if we write in this form, then this equation can be written in this way. Just let me clean this. Then we can write, instead of E, we're gonna write ex vector, ex I cap plus ey z cap plus ez. Okay, just wait. Okay, ez k cap. We can write this way, and this del operator is nothing but this one, del x I cap plus del y z cap plus del z k cap. We can write this. Okay, then instead of h, what we can write h x I cap plus h y component, this one, j cap plus, and z component of h, that is your k cap. Okay, we can write this way, right? So this is suppose equation number 4. Now let's evaluate this. So let me copy this left hand side. Okay, and let me take a new slide here, this one. Okay, how to find the cross product of this? This is nothing but what? This is nothing but E cross not E cross, del cross E. This is nothing but del cross E, right? So this is what we have, del cross E. Okay, let's evaluate this del cross E. So here, how to evaluate this cross product? So I cap, j cap and k cap. So del x, del y and del z. Then here we have ex, ey and ez. So being the student of BSc, hope you know these kind of things. I don't think I need to explain in details. These are very basic mathematical concepts. So now, so for I cap we have to take these two, then these two, right? So what ignorate I cap, then so del y this. Now you see, here we have considered that these two waves, electromagnetic waves, are propagating along x-axis, right? This is electric field and this is suppose magnetic field. Both are perpendicular, mutually perpendicular, and they are these two this EM wave is traveling along x-axis. So you see, that's why what we're gonna have here, the derivative of Ez with respect to this, that's gonna be 0, and similarly del z of del y, that's gonna be also 0 because it is propagating along x-axis, right? So hope you have understood this. So that's why what we're gonna have 0 minus 0 here. So next minus j cap, then for j cap this one and this one. So del x of Ez, then minus here again del y of ex, sorry, not del y, del z of ex. Okay, so again here it is del z, so that's why it's going to be 0, right, as it is propagating along x-axis. So hope you have understood this. So now you see, then plus k cap, so plus k cap. So now for k cap, what we're going to do, we have to operate this one by this one, that is del x of ey, then minus, then operate this one by this one, del y, so that's going to be 0, right? Hope you have understood this, right? So here what we're going to have from this result, we're going to have del cross E, that's going to be equal to, that means this one is equal to nothing but here we have got minus del Ez by del x j cap, then plus del x of ey k cap. That's what we're gonna have. This is suppose equation number what was the last equation? 4. Now this is 5, equation number 5. Okay, now you see from equation number 5 and from equation number 4, here you see, let me copy this equation number 4 and let me write here. Just give me a second. Okay. Sorry. Okay. Now you see equation number 4 is this one. So now if you compare this, here you see this is the left hand side. Okay, on the right hand side, here we have no I cap, so that's going to be 0. So this one and compare this one and this one. Okay, so from these two equations, equation number 5 and 4, what we're going to have, this is equal to hy, not only hy, mu naught del del t of hy, right? That's what we're gonna have. What we're gonna have? We're gonna have minus del Ez by del x is equal to minus mu naught del del t of hy. That's what we're gonna have, right? So from equation number 4 and 5, from equation number 4 and equation number 5, so what we're gonna have, we're gonna have minus this minus of this one is equal to this. That means mu naught minus mu naught del del t of hy. That's what we're gonna have, right? So we can write that minus this is equal to minus mu naught del del t of hy. That's what we're gonna have. Minus minus gone, right? So that implies del E by del x is equal to mu naught del hy by del t. That's what we got. And what we're gonna have, and if you compare this one with k cap with k cap, then you're gonna have this one is equal to mu naught del del t of hz, right? So we're gonna have del del ey is equal to minus mu naught del del t of hz. That's what we're gonna have, right? So let me write on the other side. Sorry. So then what we have got? We have got this. So let me write it properly. Minus mu naught del del t of hz. That's it, right? So that's what we're gonna have. Okay. Now you see we have considered that E x comma t is equal to E naught e to the power I kx minus omega t, right? That's what we have got, right? So then if we take the y component, then what we're going to write? Then we're going to write here E naught y, if we take the y component, e to the power I kx minus omega t, right? Then on the other side here we're going to get mu naught del del t. Similarly we have h x comma t, so h naught e to the power I kx minus omega t, right? So here we're going to get a z component of this, right? H naught z, and we had taken here phase defined alpha, so that's why what we can do, we can write this H naught z e to the power I kx minus omega t alpha, not z, phase difference was alpha. We can take this, right? Now you see, if you differentiate this with respect to x, then what you're gonna have, this E naught y is constant, and derivative of this is again e to the power I kx minus omega t, and it is function of function. If you differentiate this term, then you're gonna get k, right? Not only k, I should be also there. So that's why what we can do, we can write here I k this. Then on the other side, right, minus mu naught. If you differentiate with respect to t, so here h naught z is constant, right? So let me write this one here, and e to the power I kx minus omega t plus alpha, we know that derivative of e to the power x is e to the power x, right? But if we have, instead of x, if we have suppose mx, then this m comes here, right? So if we use that concept here, you see here this is function of x, this is function of t, and this is constant, right? So if you differentiate this part within the bracket with respect to t, then these two gonna be equal to 0. Then if you differentiate this, then you're gonna get minus omega. So here we're gonna write minus omega, and this minus gonna be plus, right? So hope you have understood this. This minus gonna be plus, right? So that's what we're gonna have. Not only this, here I also there, I should be also reading. Hope you have understood this, what we have done. So what we have done, this is constant part. If you differentiate this, derivative of ddx del x of e to the power I kx minus omega t, del x of e to the power x is simply e to the power x. According to that, we're gonna get e to the power I kx minus omega t. But here you see, here it was x, but here we don't have x only, it is function of function. So again you need to differentiate this I kx minus omega t, as this is function of t. So derivative of this with respect to x, that's going to be 0, and derivative of x with respect to x is 1. So here we're going to have I k only. So that's why this I k comes here, right? And this is constant, so that is written outside the differential coefficient. So hope you have understood this. Similarly, we have done here also. If you differentiate this with respect to t, e to the power I kx minus omega t plus alpha, then what you gonna get? Again you're gonna get e to the power I kx minus omega t plus alpha. Then again you have to differentiate this, and if you do that, then here is the function of t only, omega t. So minus omega comes out, right? And there is I, so minus I omega. So because of this minus, and there is already minus, so that's why we have got plus here, right? And this I is there, okay? So hope you have understood this. So here you see I cancels, right? So what we have got k e naught y e to the power I into kx minus omega t is equal to mu naught omega h naught z e to the power I kx minus omega t plus alpha. Now let me copy the system and let me take a new slide. Okay, let me take a new slide. So here is the last step we have got. Now you see, we know that e to the power I theta, it can be written in this way, cos theta plus I sin theta. This is the real part and this is the imaginary part, right? If we take the real part only, taking real part, you see this part can be written as cos theta means kx minus omega t here. Instead of theta we have this, right? And plus I sin again kx minus omega t. That's what we can write. Now take the real part only. Okay, so hope you have understood this. So then what we're gonna have, k e naught y cos k x, that means we are taking the real part of both sides, okay? And on the other hand, this one omega h naught, so here sine instead of theta, not sine, cos, we are taking the real part, okay? Here instead of theta we have kx omega t plus alpha. Now you see, these two gonna be equal when these two are equal and these two are also equal. Suppose we have k e naught y equal to mu naught omega h are equal, and this is possible when these two are equal, okay? And these two can be equal, okay, when kx minus omega t is equal to kx minus omega t plus alpha equal. Okay, these two are equal, and it is possible only if alpha is equal to 0, right? Hope you have understood this. So what we're going to write now, you see, this equation will be true for all the values of x and t if this phase difference alpha is equal to 0. So thus so E and H must be in the same phase. If they are in the same phase, or then we also can write that E or N B are or must be in the same phase. This is proof. And again we are also we are to solve so these two are in the same in constant ratio. You see, if this phi is equal to alpha is equal to 0, right, alpha is equal to 0, then from this equation we can write this as equal to 0, then we're gonna get this equation. Okay, we're gonna get this equation. So now you see, from here what we have got, these two cancels, so E naught y by H naught z, that's gonna be equal to mu naught this by k, right? That's what we get. And you see, if you multiply this mu naught here, then what you're gonna have? Then you're gonna have this mu naught H naught z by k, and in that case you can write this one as b naught z. Okay, so if you don't write this one, then you can keep this way also. So now you see, so therefore the ratio of amplitude, of E and H, that will be given by E naught by H naught, which is going to be equal to again E naught y by H naught z, that's going to be equal to mu naught omega by k. Okay, now you see mu naught omega by k, then this omega by k is the speed of wave, and in free space this is going to be equal to c. This is going to be equal to c. For free space, that omega by k is equal to c, which is the speed of light. That means EM wave travels with the speed of light in vacuum. Okay, we can say that. And so therefore or we can say that this is E naught by H naught is equal to constant. This is equal to constant, and hence that E naught by B naught will be also constant. That will be also constant. So hope you have understood this. Because you see, if you multiply this mu naught with H naught, then you're gonna get B naught, right? Then C is nothing but that's gonna be constant speed of light, right? And here you see, so here you may you may think that if I have written here E naught and H naught, then where I have written E naught y and H naught z, Now you see we have obtained in this equation, you can see though we have obtained E naught y and H naught z, we have obtained this relation from this one, after here after you see what we have done here. After simplifying this equation, we have got this result, right? We have got this result. Then we have compared this components, right? So here you can see that these are nothing but you see this H naught, and here you see these are nothing but amplitudes, right? Amplitude. So just let me explain in very simple manner. So this is the electromagnetic wave support, right, moving in x direction. So this is the max so this is the maximum displacement. This is the if this is the electric field, this is the amplitude of this electric field. Okay, so this is along y axis, so you can write e naught is equal to e naught y, right? And this is along z axis, so you can write H naught z, right? So obviously these two H naught and E naught by H naught definitely equal to E naught y by H naught z, because here you see these two are oscillating in this y and z direction. Magnetic field, wave is propagating along x direction, and but magnetic field and the electric field electric field and magnetic field are oscillating in y and z direction. So that's why these two must be equal to this, right? So hope you have understood this. So thank you for watching. See you in the next video.